So now that we've looked at synchronized methods, let's turn our attention to synchronized methods' younger sibling, which are synchronized statements. And as you'll see, synchronized statements can also be used to provide Java built-in monitor objects with mutually exclusive access as well. And just as with synchronized methods, synchronized statements can be used to protect shared mutable state from corruption due to concurrent access by multiple threads. So as we saw when we talked about the limitations with synchronized methods, these approaches can incur several constraints. For example, they can yield excessive overhead due to coarse-grained serialization because synchronization occurs at the method level, which can be good from a simplicity and understanding point of view, but it may not be the most effective way of being able to have code running concurrently. Another problem that we talked about was it always synchronizes on the one and only implicit lock, which is often this. So you're stuck with, actually not often, it is this. So you're stuck with the object itself being the granularity of synchronization, which could easily become a source of contention if you're not careful. So let's take a look at an example. This actually comes straight out of Java and the Java class library, in particular the Java util concurrent package. This is called an exchanger. And it defines a synchronization point where threads can pair and swap elements using pairs. And I'm not going to talk a whole lot about the actual use of exchanger. It's basically a form of a rendezvous-like mechanism. But basically the idea is you can swap values. And there's certain algorithms that are concurrent that can benefit from this. What I want to focus on here is the idea of being able to have synchronized statements that are going to be finer level granularity than synchronized methods. So one way to implement the create slot method, which is one of the methods in an exchanger, would be to use the good old synchronized method approach. And in that case, everything in that method would be running in mutually exclusive mode, and only one thread at a time could be in there. The way this is going to work, as you can see, we come into this method, we make a new slot, and then we go ahead and check to see if the array sub-index is equal to null, where index is the value that's passed in to create slot. And if it is null, we go ahead and allocate the new slot to the element. So this is what's sometimes called lazy initialization. A more effective approach, or potentially more scalable approach, is to synchronize at the individual statement level. So rather than synchronizing at the method level, this time we're going to change things. So we only synchronize at the statement level. So we're only going to synchronize when we actually need to come along and check to see if the indexed location in array A is null. Because the other parts of the method, the parts up here that are the new slot part and the final slot array A equals arena, those things are not going to be corrupted because they're not using shared mutable state. They're using final variables for one thing. So in this case, we're just going to synchronize a very narrow part, a very limited scope here. And therefore, synchronized statements can be used at a finer level of granularity than synchronized methods. So they're very, very fine-grained, and that allows more concurrency in the system because the scope over which a lock is held is limited. So the way this works is we come in, create the slot. That doesn't have to be protected. And then we go ahead and synchronize on this. Now, in this particular case, we're synchronizing on the intrinsic lock. So that's a common way to do things. But we can also synchronize on an explicit object. And that's one of the nice features you can use with a synchronized statement. You don't have to synchronize on this. You can synchronize on something else. And in this case, the something else that we're going to be synchronizing on is this array called arena. And the arena is going to allow us to have a different way of synchronizing that's not this. And that avoids the problem we showed earlier when we talked about limitations with synchronized methods, whereby another thread can block that method from making any progress just by synchronizing on the object. And this is very useful when the intrinsic lock is either too limited or too contended, or we don't want to let the synchronization properties leak outside of the object itself. So that's just a quick example illustrating how you can narrow the scope over which locks are held by using synchronized statements, and in this case also by using a non-intrinsic lock, an extrinsic or explicit lock. So let's talk about the pros and cons of synchronized statements. So one of the nice things here is it allows a private field to be used as a synchronizer, as you can see here. So by using the arena as the synchronizer as opposed to this as a synchronizer, we no longer have to worry about one rogue thread keeping thread T1 from being able to access its critical section, because we're not synchronizing on the object, where the actual implementation is synchronizing on a local field, which is not visible to anybody outside of that. Of course, there's always downsides. The main downside is the syntax is a little bit more convoluted, because now you've got these synchronized statements that are showing up inside of methods. Honestly, not the end of the world. So, but if you look at the code, you can see that there's a bit more syntax going on here for synchronized statements than there are for synchronized methods. What I'd like to do now is talk about how you can use synchronized statements in a more interesting way to implement something called the double-checked locking pattern. And double-checked locking is another pattern that I wrote about many years ago, and it appears in the Posted 2 book. You can also read all about it, and it's very controversial history at the link below. It's kind of fun. Synchronization with the double-checked locking pattern is done lazily when initialization is first performed. And that's basically what's going on here. So you can see double-checked locking is happening in the exchanger class in the Java class library, such that we are going to do it in such a way where if slot equals null, that's the part that's in the lower right-hand corner of the slide. If slot equals null, then we're going to call create slot, and only on the first time in will we have to synchronize on anything. But this check up here where it says if slot equal null, that particular check is not done with locks held. And the reason that this all works is because of the fact that it's using final variables here. But that's the double-checked locking optimization mechanism. And there's no need to synchronize the check here if slot equal null. And that's because reads and writes to references, which is what slot is. Slot, as you can see, is a reference to arena sub-index, are always guaranteed to be atomic. That's just part of the properties of the Java memory model. And therefore, we only create a new slot if the current slot is null, and we only synchronize when the slot is first created. So create slot is called when slot is null, and we synchronize in that case, and then we check to see if it's null. And if it's null, we go ahead and assign the new slot to it. So just kind of illustrating how the double-checked locking optimization pattern is actually applied in the context of the Java class library. So that's the end of our overview of Java synchronized statements. So at this point, you should know what a synchronized method is. You should know what a synchronized statement is. And when you do assignment 3B, you'll get a great opportunity to show off your newfound knowledge of Java synchronized statements in some very interesting ways involving Java built-in monitor objects.